afternoon. I'm Whitney Mason. I am currently the Deputy Director in the Strategic Technology Office.
And I'm Stuart Young, and I'm a Program Manager in the Tactical Technology Office.
Welcome to the Future of Autonomous Vehicles Technology panel. We think this is a super timely topic. Right now, there's a lot of research being done in both commercial and academic worlds, thanks to applications like self-driving cars, drone delivery of packages, even the automation of our offices and homes. But DARPA has been thinking about this for a really long time. There have been at least 65 programs with the words autonomy or autonomous in them, including the Autonomous Land Vehicle program in the 1980s, and including the DARPA Grand Challenge and the DARPA Urban Challenge that Stephanie talked about yesterday. There have also been lots of programs in sensors and algorithms and platforms. But from our perspective, we're not quite there yet, right? So this panel is about thinking about what we can do. Stuart, you have ongoing programs in this area. Where do you think we are now, and what are the challenges you think we need to address?
Yeah, thanks. So I run one of the programs I run is the RACER program, or Robot Autonomy in Complex Environments with Resiliency. And in RACER, we're fundamentally working on solving two problems, that is speed and brittleness. Currently, robots are too slow to be operationally relevant on the modern battlefield, and they're too brittle. They don't adapt well to domains outside of their training sets if they're using neural networks. And so consequently, autonomous maneuver is not mature enough for the services to consider as part of their operational concept. We operate in a tactical environment against an adversary as well. So we like to say that the adversary gets a vote. So we have to be able to not only go from point A to point B, but we have to do it mindful of what the adversary might not want us to do. We are leveraging what we can from the self-driving community that you mentioned, things such as sensor development, experimental methodologies, and the use of simulation. But fundamentally, our problem is different than the self-driving car environment, where our environments are devoid of structure that they daily depend on for their solutions. We're also looking at a bit different problem in the sense that we have to reason about the terrain in front of us every step of the way, whereas on the self-driving community, that's not the problem. You know, they pretty much know the road networks and where they can go, but they're looking out for, dynamic actors. So in some sense, the problems are different. Some of the things we're learning as in the program, though, is really exciting, is that we're learning to adapt to the environments faster, which is something that I really wanted to create in the RACER program. We're learning to do adaptive parameter tuning. As we get to environments, we can quickly adapt to those environments, as well as the importance of the interaction between the traditional perception, planning, and control components. We've also learned that we'd like to use simulation, like the the self-driving community. But we've also found that there's been challenges for us in that domain because we lack structure and the interactions we have with the world. Simulation is not quite where we need it to be. So we use it as part of our workflow, but it's not to the point where we'd like it to be. So we still there's a lot of work for us to do there. Additionally, there's some, more things that we're not doing in the program, such as new sensors. I know that's an area of interest to you. RACER is not focused on developing new sensors, new platforms. It's focused on the autonomy specifically. There's also a lot of work that needs to be done in trust and interaction and safety and those types of things. And so we're not working on them directly, but we are mindful and we leverage what we can from other programs like Assured Autonomy and DARPA. We're also looking at teaming. Human-robot teaming issues are not something that we are specifically focusing in RACER. As I mentioned, it's a foundational problem that we can then be one of the building blocks to build things up. We're also not looking at TEV&V so much, which is another area of interest. Data is always an issue. Don't want to talk about that too much. It's something that we're trying to wean ourselves off of. But I think this is an area where simulation could contribute more as we move forward. And then finally, shout out to my colleagues in DARPA, Ted Senator and Ceylon and others. We're not working on the fundamental learning and AI techniques directly, but we are actually contributing to that as we continue to learn in the real world. We're doing it out of necessity for our problems. And then finally, I just want to mention cybersecurity. General Shaw talked about that this morning. It's always of interest, but Sergey and others in DARPA are working on those parts of the problem. So it's a community effort to solve this holistically, and RACER is just one part of it. So.
Very cool. Thanks, Stuart. These are all really great challenges, and it won't be surprising to the audience to know that we've assembled the perfect panel to help us discuss many of these questions. So let's bring them up. First, we have Lieutenant Colonel Chris Orlowski. Chris is currently the product manager for robotic combat vehicles in the United States Army Program Executive Office Ground Combat Systems. Chris and his team are responsible for the super hard challenge of executing the hardware and software programs that will eventually deliver the robotic combat vehicle family of systems. Chris has a Bachelor of Science in Mechanical Engineering from the United States Military Academy, a Master of Science in Astronautical Engineering from the University of Southern California, and a PhD in Aerospace Engineering from the University of Michigan at Ann Arbor. He also has a DARPA heritage, serving as program manager in both the Biological Technology Office and the Tactical Technology Office. Next, we have Dr. Eric Krotkov. He is currently the president of EK Consulting AI, providing advisory and consulting services in artificial intelligence. Prior to that, Eric served as the chief science officer of the Toyota Research Institute, where among other roles, he led exploratory research efforts in automated driving, robotics, new materials for batteries and fuel cells, and machine-assisted cognition. Eric also has a DARPA heritage, serving as program manager in the Tactical Technology Office. And then he was at DARPA for another 15 years, consulting on various projects, including the DARPA Grand Challenge and Urban Challenge. Eric got his PhD in Computer and Information Science from the University of Pennsylvania. Next, Professor Deva Ramadan from the Robotics Institute at Carnegie Mellon University, and the director of the CMU Argo AI Center for Autonomous Vehicle Research. His research interests span computer vision and machine learning with a focus on visual recognition, something very near and dear to my heart. He's been recognized with numerous awards and Best Paper awards, serving as editor for at least 2 technical journals, and sits on the committee of numerous conferences. And finally, Dr. Claire Tomlin, who is chair of EECS and holds the James and Catherine Lau Chair in Engineering at UC Berkeley. Claire got her PhD in EECS from Berkeley, and then was at Stanford for about 10 years, holding assistant, associate, and full professorships. She has returned to Berkeley, where she works in hybrid systems and control, and integrates machine learning and methods with control theoretic methods in the field of safe learning. She works in the fields of air traffic for unmanned air vehicle systems, and for something completely different in systems biology approaches to cancer. Claire has been recognized with numerous awards as well. Welcome to you all, and thank you for being here.
So I'd like to start off with a few questions for our panelists here, and then we'll take questions from the audience as we proceed here. So the first question I have is for Chris. What autonomy can we say is fielded by the services in the ground domain, and what are the barriers that we still face in being able to field those systems?
Well, thanks, Stuart. Well, good afternoon, everyone. So fielded autonomy, at least in the Army, is very limited right now. Those are familiar with PackBots or Talons, which Eric started as a tactical mobile robots program about 2 decades ago. I had the privilege of leading the organization that sustained those robots in Afghanistan about a decade ago. Those robots have some limited room mapping, SLAM capabilities, but are primarily focused on what we call civil support teams, which are those teams that in case of a chemical, biological, or nuclear attack on the homeland, they would deploy to support those, to support that map, sense where the radiological effects are and things like that. That's about it. We've done a lot of experimentation, years of DARPA programs, years of Army programs, limited primarily to an operational deployment of what we call leader-follower, which the name is transitioning to a new name now, but really a truck leading other trucks, but those trucks are unmanned. That's been ongoing at a couple locations in the US. And then really some limited experimentation. So the office I have, we have to transition these capabilities, but it's a robotic combat vehicle experimentation just concluded at Fort Hood just a couple weeks ago, actually, and has some limited waypoint following and navigation, but that's about what's been, nothing really fielded. There's a lot of technological barriers, as you mentioned at the beginning, but I think a couple that are often overlooked are safety, so safe operation of these systems. So at Fort Hood, Texas, we had a safety observer following every platform in case it had to render it safe. We need to move away from that, especially when we want to field these provably safe systems, and the future is a big challenge. Also, I think, too, just how we do things contractually. There's one thing to set up budgets, but there's another which we're trying to work, leveraging new authorities, of setting up software programs to actually start transitioning these capabilities and signal that there's an opportunity for industry to develop, to see that there's a business case where they could work with the government and work with to do off-road military-focused autonomy.
Thanks.
Eric Stewart referenced this in his opening comments about the need for simulation to meet Chris's needs. And trillion-mile reliability has been a tagline for self-driving vehicles. Have trillions of simulated miles been driven by commercial self-driving cars on the path to solve that?
Thanks, Whitney. Hello, everyone. I'm going to answer that one with the perspective of my previous role at the Toyota Research Institute, which is all into cars. So trillions, that's 10 to the 12th. Toyota makes 10 million cars a year, 10 to the 7th. We have each of them lasting something like 10 years, another 10 to the 1, and each year driving something like 10,000 miles, 10 to the 4th. Put it all together, the Toyota fleet each year is driving 1 trillion miles. During our encounters throughout the world on the roadways there of all kinds of different operational design domains, urban, suburban, rural, night, day, rain, dust storms, wind. Use your imagination. There's so many things that go on the roadways and off. And so we need to have reliability to handle all of those design domains. And we can't possibly drive all of those miles. And it's just going to take way too long. So we have to do it in simulation instead. And Whitney, your question was, have we done that? Not yet, but we are well on the way to it. And photorealistic rendering, producing the imagery that the sensors would really see, and physics engines that can model the interaction of the vehicle and the environment and the other vehicles are a main part of that. But to just add to my answer there, yes, but we're not there yet, sort of a bigger picture answer, TRI, the research arm of Toyota that's focusing right now on self-driving, has graduated all of the engineers who have been working on that out of research, DARPA's domain, and into development. A new organization inside DARPA called Woven Planet. So we don't really consider it a research problem anymore. Just like DARPA does TRL-2 up to 6, so does the Toyota Research Institute. So it's now really a development problem to use those tools and get the trillion-mile reliability.
That's really cool.
So I have a question for you, Deva. So are stable interpretations of a dynamic world a factor in military applications of autonomy? And you've spoken about this before in previous work, and I'd like to get your opinion on how that translates to our off-road domain that is replete in the military environment.
Definitely. So maybe I'll start by giving you a little bit of context around, I think, the question. So I guess one of the interesting things about working in the self-driving space is that the failures that have already happened are quite public and well known. So I actually feel like it's a good opportunity to sort of look at even the popular press that you might see about cases where things haven't worked out well. And one of the lessons that at least I've taken from looking at those cases, where it seems like oftentimes it's a failure to really understand geometrically what's happening in the world around us. And it's also something from the fact that if the world was still, it seemed like it'd be much easier to understand. But because the world can change, now this estimation task becomes much more difficult. And I think one of the crucial reasons why the world can kind of change on a dime is so from my own background of computer vision and perception, I would use the term occlusions. So things can appear from behind a wall or behind an occluder. And what that means is that before you didn't think something was here, and now sort of a split second later you do. And so being able to deal with those really possibly dynamic changes, but doing it in such a way where you still build almost a stable interpretation of this dynamic world. It seems really difficult. So that was really the sort of motivation for calling that out. It was almost sort of a bit of navel gazing at the failures of the industry from my own, I guess, personal perspective. And then really getting to the question that you're asking, which is, okay, does that really transfer over to military applications? And I would say yes. One of the things that you mentioned before is autonomous systems possibly or probably have to reason about adversaries. So you're sort of not out there in the world alone. And so you have to sort of figure out how other things are moving, and if they're really adversarial, that makes it all the more difficult because maybe they want to move in a way that doesn't make it easy for you to sort of figure that out. That said, I think that sort of Racer I find super intriguing. We were talking about this earlier, in that it kind of carves out this space where, in that setting of off-road navigation, seems like there's an incredible sort of really nicely honed challenge there where you don't even need an adversary in there. It's still sort of like a challenging task to figure out. And there it seems like the crucial thing is not just estimating the state of this mostly static world, but really estimating traversability. But I'd love to hear your thoughts on that, I guess.
Yeah, I totally agree with you. This is, one of the biggest problems I feel like that we're tackling in Racer is, and it's related to the topic, which is why I was so fascinated to ask you this question, is because we're obviously having to constantly deal with uncertainty in the environment that we deal with, and how we reason about the uncertainty, but what we see, what we don't see, and of course Racer is about trying to drive faster, and of course we're somewhat too myopic to be able to make those decisions far enough out to push those speeds. So. And then I know that Racer is largely, metaphorically we were talking about, it's like the robot against the environment, but that's only part of the problem. And that's not sufficient. That's necessary, but not sufficient to meet Chris's demand signal for us. So,
Gosh, Claire, this just makes my question all that much more important. So I'm going to quote from a talk I watched you give, and you said, "We want our autonomous systems to operate safely in real-world environments." And I told you, I bought a Tesla, and I would love to let my Tesla drive me to work like some of my friends, but I'm terrified. So how do we achieve safety in real-world environments, and what research is ongoing, and what else do we need to do?
So I think you're terrified because you know too much about the sensors, right? So thank you for that question, and thanks for the invitation to participate in this panel. I think that people trusting autonomous vehicles, there's a combination of many things, but I think two key things there are the understanding that the engineers that have designed these vehicles have done a very good job in designing it, and there has been a kind of verification and validation process that's gone on. And there's a whole, as we've been hearing about through these last 2 days, there's a lot of work going on in verification and validation, in computer-aided verification combined with control theory, that is being used in the design of autonomous vehicles. But it's more than that. I think it's that combination of mathematical methods from modeling and verification with a kind of experience with the data, with the experience of being in the car and observing it maneuver in a way that either you would have done or you wouldn't have done, and you like the way the car did it better. So that is, I think that we're not there yet. I know we're not there yet. But I think in terms of the verification and validation, I think that in the near future, we will be able to perform this verification and validation in the kinds of limited operational design domains. We can put constraints on these environments, and we can prove something about how the system will behave under those constraints if the environment satisfies what these constraints imposed on them. But that's not always going to be the case. So it's really that combination of capturing a lot of data, new data about how people behave under, not just sort of the data of the past, but how people adapt their behavior as autonomous systems are fielded. And we're just not there yet. So I feel trust combines verification with a lot of work going on in data and data distribution and understanding how that's incorporated. And I think that the autonomous driving world is doing that in a very interesting way. And I think that there's the ability to sort of put out a Tesla and say you're not allowed to, the human is in charge. You're not allowed to drive it on autonomous mode. But many people are, and there's a lot of data being collected on that, especially in California. So I think that it's an interesting way to field a system, and I think that it's actually really contributing towards the data that we will need eventually to be able to achieve trust.
Yeah, thank you for that.
So we look forward to seeing some questions come in. I have one question that I'd like to ask. I feel like we heard this morning from Lieutenant General Shaw from Space Command, and so I'm going to take advantage of what I heard from him and pose his question, I think, to the panelists here. So he discussed the importance of autonomous vehicles in the space domain, and when discussing autonomous vehicles with my colleagues at DARPA, I'm a ground autonomy guy generally, talking with my colleagues who are focusing on underwater or maritime. One of the things that I found really interesting and insightful was, in some sense the problems are the same, but they're completely different, right? So, perception, planning, and control, but the modalities that you do, these different sensing modalities are completely different. So with that in mind, and General Shaw's question to us is, how do we see the challenges of autonomous vehicles in space affecting future efforts that we need to be looking at? So this is a question for the whole panel here.
I'd jump at that one.
Sure.
So one of the key attributes of operating in outer space is that the communications bandwidth and the latency are both terrible. So there has to be a lot of intelligence on board. You can't phone home, or if you do, it's going to take a long time to get the right answer. So there needs to be enough onboard decision-making to be able to handle some of the basic scenarios when you lose contact with the remote system, so that it can stay safe and yet still make some small progress towards the mission goals that it has. And that was very much the same principle, terrible communications, that we imposed during the DARPA Robotics Challenge back in 2015. The scenario was robots trying to respond to a Fukushima-like nuclear disaster. And it was incredible how much onboard decision-making could be done. And a very small number of bits going up to the remote system still allowed progress to be made. So I feel like that paradigm is no different for underwater vehicles, surface vehicles, ground vehicles. Just the amount of terribleness on the comms is the variable.
Thanks, yeah. Can't believe it's been 7 years since DRC. I miss those days. Anyone else want to weigh in? Claire?
Well, I think that I've done a lot of work in air traffic and in autonomous air vehicles. And there, just like Eric brought up, the safe mode. If there's a communication that's lost, or if you can't, for some reason there's an inability to change the behavior of the system, you really have to demonstrate that there's a safe mode that the system will go into. And that doesn't just mean a safe mode for its own behavior, but also a collision avoidance with respect to other vehicles. So that's something that has to be demonstrated. And I think that with the space domain, which I don't know a whole lot about, but it really ties onto this idea of having the vehicle operate safely with respect to itself, with respect to other things around it, even when you can't change its current behavior.
Absolutely, yeah.
To start with, pull in one of your other programs that you've worked on, and many, others have Dan and others have worked on, Dan Pat and others have fact. So like the Alias program, unmanned helicopter, it's really, like you've told me, it's an expert system, right? And we've talked to them. We've actually visited Sikorsky, my team and I did. And it's like, yeah, they're starting to get FAA certified for LiDAR, but they laughed when they said, we didn't bring it up, but they did. Good luck trying to do that for computer vision. So when we start taking some of those problems to the ground, how are you going to provably correct and get the thoughts panel to, how do you prove that system is going to operate safe? And we need to be careful in the Army. We need to take appetite suppressants on solving the right problems first. What's the appropriate operational design domains that we can transition first?
Right.
It's probably systems not operating around other humans. Probably. Maybe soldiers that you tell them, don't get close to the robot, don't get comfortable, which is a continuous problem. Future, yeah, maybe in an urban setting we can have robots moving between people, but I think we're pretty far from that. So just curious to pull in some of those thoughts of how we can start looking at helping. I mean, it's not just going to be our systems, it's going to be all domain systems are going to have that.
Yeah, absolutely.
Maybe I'll throw out two comments as an outsider who hasn't really thought about space, but maybe talk to some colleagues who've looked at that, who are in that space. So one perspective is that it seems like, okay, in addition to the bandwidth limitation, it's incredibly resource constrained in every which way. So you can't switch out a battery easily. You can't, switch out a storage drive. And so the fact that the resources are so limited, I think, poses challenges that to the sort of the infrastructure aspect of it, which at least this seems quite daunting to me. And then the other perspective that I kind of value as a perception person that is somehow very data-driven is the ability to collect lots of data, both for validation and for testing and maybe even for training. And it seems like that's also really difficult in the space domain. Yeah.
Absolutely. Yeah, thanks.
So when we started talking about this panel, I'm going to ask the question that I really wanted you guys to answer because this is my love, which is sensors, right? So do we have the right sensors? Do we need advances in sensors? Should we use the same old ones that we always use? Do we need to think about using different sensors? Should we be like Elon Musk and throw everything away about the vision, which I do vision for a living, that's no. What should we do? And does it matter, right, in different domains? Does it matter off-road versus UAV, et cetera?
Okay, I'll do it. I would contend to help deal with the safety aspect of it. I would want to. There's a colleague in my department, Srinivas Narasimhan, and he makes a statement that roboticists love to over-censor, meaning that it's you want to sort of cover as much as you can of the world around you, and moving around with a blind spot is scary. Even when I drive with a blind spot, it's really scary. So there's this tendency to kind of want to over-censor, and I actually think, from my perspective, that's even the right thing to do, because you get redundancy. As you're deploying things that are still sort of on the bleeding edge, that seems, I would think you want to err on that side. That said, the other sort of personal inspiration I have for this sort of stuff is I still want to, oftentimes I find myself thinking, well, how am I able to drive and, operate something that's moving at 60 miles an hour, even though I probably biologically wasn't tuned to do that. And so for that, it does seem like vision is a primary sensor. So I kind of personally think that maybe we could eventually get there, but I think the path to get there, I would try to lean on as many other sensors as possible.
Yeah, so fair comment, but you don't drive 60 miles an hour in the snow or the rain or the fog, right? So I always assume that other modalities augment, right, what we do with our eyes. We know that people have five senses, right? We're connected, and I'll even talk about, the Eric and I were talking about this yesterday, the ookie feeling, right? Like the kid that's walking down the sidewalk and he's going to cross the street, right? Your sensor doesn't know that. Is there, or at least your vision sensor doesn't know that, right? What other modalities can you have in there to make up for the hairs on the back of your neck?
So I don't know if I'd call this a sensor, but it is a modality. I think this area of behavioral modeling, so having the robot, the vehicle, the autonomous system, be able to take cues from other vehicles or other people, pedestrians around it, and to be able to have a trusted behavioral modeling paradigm. So to be able to predict, at least for the next few seconds, which are most important, what that vehicle, what that person is going to do. And I don't think we're there yet, from my understanding of what is being done in behavioral modeling at autonomous vehicle companies. I think there's a lot of work going on in this area, but being able to make predictions and then update those predictions in real time, so that taking in data of what the other vehicle or the person is actually doing is really important in being able to sort of proceed in a world where we have autonomous cars interacting with, well, pedestrians, but also human-driven cars.
Right.
Can I just add to that? I couldn't agree more. When I heard your talk yesterday, I was inspired. When I heard Bart Russell's talk yesterday about behavior modeling from the point of view of a cognitive scientist, I was floored. One of our biggest problems in self-driving is in the driver's seat. And being able to understand their situation awareness, where are they looking? Is it down at their phone or is that at the scene? Do they see the car that's merging into the side of them? Being able to understand the driver and the behavior, not just of them, but the other cars around them is very, very important. But that's not a sensor. And coming back to the more the merrier. At the research stage, we should continue to be looking for sensors that can see through foul weather. And then in the development and production stages, you've got to choose. You can't put a roof rack full of sensors up there. But I believe that reliability in multiple environments, operational design domains, is going to depend on the complementarity of those different sensors. So that's why the more the merrier.
Yep. Thanks.
And if I can add to that quick, I think another interesting where you could take that is, especially where you sit where I sit now, and you're looking at more what does a production system look like. We have to be very cognizant of cost. One, because attritable is not a word in the dictionary, or the Army loves to use it, but I mean, that's the intention. These platforms are supposed to be put in harm's way where we don't want to put soldiers in harm's way and take that first contact. So they need to be we define a nice balance between cost and performance. But from a sensor standpoint, we're asking a lot of things for that platform to do. So if we can look at sensors from what different things can the same sensor do, and what's the right thing to optimize for, or what's the most important thing. It might be computer vision if it's a ground autonomous vehicle, but maybe it's really, we want that sensor to detect potential threats, and then the computer vision is going to take a backseat. I don't know which one should be primer over the other, but that's one thing. If we can do more with the same sensors and just have more processing, I think that's something that we could would be an interesting way to.
And then just to add on to what Chris said, I think there is a real trade-off between sensors and comms. So how the communication network is going to evolve, what will be communicated, what about intersections, what will be communicated. That is a trade-off, and I don't think we're there really in understanding that yet.
Yeah.
So I'd like to just kind of do a follow-up on the sensors question you asked, Whitney. I think this is probably mostly for you, Chris, but I think everyone can weigh in, and that is, I've been talking to a lot of warfighters, and specifically on the sensing modalities, they're unimpressed with our active sensors that we use on robots, lasers and stuff. And so I don't know if it's coming from Elon Musk's comments about everything vision, but certainly from a warfighter's perspective, it's fair to say that they don't want to light up the battlefield like a Christmas tree with all their active sensing. And so I think there's a lot of room for potentially sensors in the passive domain, and wanted to get your thoughts on that. Or I know there's a lot of work going on in DARPA and other agencies, and also in academia. So I just want to get your thoughts, Chris, or others on that, and then maybe Deva, how that maybe changes our perception problems with those sensors.
So I'm going to steal General Shaw's comment since you referenced him earlier. I think we're very much with our robotic combat vehicles. The Army is learning how to use them. So one of the things we're setting up is continued experimentation. How do we want to use these platforms? And so I think we should use whatever we have available to kind of follow on Eric's comment until we kind of get a sense for what we can. And then we can design, and maybe it's research that needs to do this first, war reserve modes or times where we're not continuously pulsing, but maybe we're iteratively pulsing, whatever it may be, as needed, which is probably a research problem. But I would also, maybe I'm on an island by myself on this one, but I'm not convinced that the LiDAR sensor on an RCV is going to be the first form of contact for an RCV. Right? We're going to primarily teleoperate these systems. We're primarily doing that in C-band right now, or depending on frequency, LS or C-bands all go pretty far away. Right? So the adversary is going to detect those platforms are present before maybe farther than when we actually see the LiDAR. So I would say we should push this forward as much as possible to get autonomous capability out there, and then we can always trade off what sensing modalities we want to do once we have it.
I agree.
Yeah, I don't know if I have anything to really add to that. So that was a great observation. I confess I didn't really thought about that. That active sensing sort of illuminates the sort of surrounding environment. If you don't want to be noticed, that's not a great strategy. And so what Chris was saying was that maybe sort of being smarter about when you throw light out. There's certainly the area of smart sensors is definitely also sort of sort of a burgeoning field.
Yeah, Stuart, let's take a question from the audience.
Yeah, great.
How do autonomous systems figure into future force design strategy? That would be you, Chris.
So that's a great question. So that's one of the things that we've experimented with. The Army has at Fort Hood, Texas, just last month, Fort Carson, Colorado 2 years ago, and we'll continue to do so. Is the initial entrances looks like the initial assets are going to be reconnaissance or surveillance assets on the ground, primarily. Not primarily is not the right word, but it gives more persistence than UAVs will be. I mean, that's at least the goal. So some small numbers of RCVs in a reconnaissance formation is at least our initial thought. I think what will happen, this is just my opinion, so I don't take this, if you read your tank destroyer history from World War II, very much parceled out to individual units, and that's some of the soldiers' feedback. I don't think, at least in the next 10 to 20 years, robotic combat vehicles will fight as a unit by themselves. They will be in 1s and 2s and 4s or something like that, integrated into units to augment their capabilities. And really, I think where they offer promise is the ability to bring payloads that we can't put on a manned platform today because we don't have the size, weight, power, capacity to do so. Things like electronic warfare, things like counter-unmanned aerial systems, we just don't have enough force structure in the Army to give every company, battalion, brigade sufficient counter-UAS or EW coverage to really protect them. And I think RCVs or other systems like that can also offer some advantages for that in the future. And that's where we're going. That's where we think we're going. But we're going to need a lot of work to get there.
One of the premises of that question, had the word autonomous. How comfortable are we going to be in sending just a bit or a few bits to the machine and then letting it on its own for an extended period?
It's a great question. I think we're pretty far from that right now.
Yeah.
We worked on some other SIBR small business work last year. A lot of questions like, well, logistics related. A lot of people were asking, well, they're going to be out alone and unafraid. It's like, no, not for a while. They're largely going to be within custody of a control platform for the foreseeable future. But that's an interesting question. I think to the trust point, though, soldiers are going to have to trust the system. But I also think we have to do our due diligence and train the soldiers properly on the capabilities and limitations of the system so they employ them effectively. And then they'll probably come back with some ideas, which they did at Fort Hood, on ways that we should employ them differently than we were even thinking. So it's always...
Chris, can I ask a question that tags onto that? Because working in air traffic for a long time, a lot of the technologies that are used in advanced civilian aircraft have been field tested in the military. So it's field tested through really trained, again, somewhat scenarios that you can kind of put a box around the environment and used with these very well-trained pilots. And then after years of training in the military, they're brought into civilian aircraft. Is that how you see things now? Is it different now, or is it still that kind of?
I think we're just really nascent and where we're going to go with these types of systems. And I've had conversation with our partners in the Ground Vehicle Systems Center and other Army development communities. Like, do we need a equivalent or an analog of flight certification for autonomous systems? Like, what does that even look like? Do we need to start what standards? We've had conversations with both internal and external groups of what's the right standards we're developing for, and are they commercial standards? Are they not? Do we need new standards? I mean, it's not standardized too quickly, right? Because we want to get capabilities out and not constrain our decision space. So there's a lot of things that and it also comes down to and this is not really a DARPA problem, but this is on our side of how are we architecting the systems from a safety standpoint? Because you can do smart things where you reduce the level of rigor you need for certain increased redundancy, and you can employ a system with much less level, in the development time, than you would if you depending on other ways you architect a system. So we got to do that smart too, but that's more just solid engineering we need to do. But we got a lot to do, obviously.
Thanks. So we have another question from the audience here. What are you doing to ensure that ethical implications of autonomous vehicles are being addressed?
So I can say that everything we've done so far, and this is actually really hard, is MIL standard 1472 Golf. There might be a hotel version now. And MIL standard 882 Echo are things that we're developing the systems by in accordance with the DoD instruction that was referenced earlier in the conference. They push very tight restrictions on the latency you can have from a control station to a weapon. It's 100 milliseconds. So everything we do from firing a weapon is in compliance with that and ensuring that the soldiers not. So we're making sure we're designing those things in now, trying to do better, but latency it's tough. I mean, 100 milliseconds is really challenging from a platform to the robot and back to be able to safely fire a weapon. So that's where we are now. Every soldier, when we've done blank firing and live firing, is in the loop, which might be the hardest problem to try to do, but that's one thing that's how we're focused on it now.
Thank you for that. Here's another. Will all or most vehicles need to be autonomous to truly realize the benefits of autonomous vehicles? And I'll add a thought to that. We were talking about comms yesterday, right? And cars can communicate between one another. But Chris's tank is probably not going to talk to me, right? So does it make it easier or more valuable to be solely autonomous on the road?
I'll start with that one. Definitely communications, vehicle to vehicle, vehicle to infrastructure, and having the autonomous systems making the decisions greatly simplifies, increases the predictability, and reduces a lot of the risks. There have been a lot of experiments with very low-speed parking lot systems where they're going just a few kilometers an hour. And if everyone's got their hand off the steering wheel, the systems, you can empty the garage quickly. So it really is much safer and easier for everybody. And if you could scale that up to, and I bet Argo has a very similar perspective, I think it would be both safer and easier for all the drivers.
Not nearly as much fun, though. I like to drive.
So I think we're getting low on time, so I think we have time for one final question here from the audience here. What technology area is the biggest barrier to widespread implementation of autonomous vehicles?
I could start.
Sure.
I mean, I have a kind of my own opinion, which is based on working in control and verification and integrating learning techniques into that, is that we are not yet at the stage where we know how to provide assurances to systems integrating learning components in the wild, right. Interacting with other vehicles, interacting with people, interacting with human-driven vehicles. And I think that it's a program where we need to bring in cognitive scientists who understand how to model decision-making, human decision-making, how we bring in, people that understand how people work together so that we can develop, effective human-driven vehicles with autonomous vehicles. So I think there's a research agenda there. I feel it's a big, I wouldn't say a barrier because that's negative, but I think it's a great thing for us academics because it's a wonderful research agenda.
Dave, comments?
Yeah, I would totally agree. I know I'm just sort of piggybacking on the answer that you gave, but I feel like how would I characterize this? To me, autonomous vehicles might be one of the earliest examples of truly safety-critical machine learning, and I don't know if there's another case of that, and I don't know if we really have the right tools to talk about assurances and how we validate an ML algorithm. I think it's very different than the way we validate traditional software systems. Like Claire, you were suggesting, it seems to be much more about you sort of have to validate the data. Have you trained this thing on enough rainy days and snowy weather conditions so that you can trust that it's going to behave the right way in those conditions? And so I think we almost need that, like a new, sort of new formalisms for validating these kinds of systems.
I'd say the biggest barriers to widespread adoption of self-driving is not technical at all. It's regulatory and insurance. And the first time a big equipment manufacturer gets sued and held responsible for harm done by their vehicle is going to be a winter. So I think those need to be addressed before it'll really take off. And if I had to pick a technology area, I'm going to say perception and stable models of a very dynamic environment. But I like the one you guys picked too.
Chris, do you have a final thought?
One, I'd even challenging more, add one level of complexity or challenge to that is, how do you do that on a platform that's not the platform you're actually going to use? So I have one of the other concerns of, this is just a thought, it keeps me up at night, but I really can't do anything about it yet, is we probably can't put all the miles we can on the actual combat platforms. It's going to be cost prohibitive.
Right.
So how do we appropriately simulate and surrogate that development on cheaper platforms and test and validate and those things to get out? I just can't see us doing it. We just don't have enough money with all the other competition we have in the Department of Defense and things we need to work on. So.
Let me say thank you. I have had enormous amounts of fun in the last 45 minutes. I hope you guys had enormous amounts of fun too, and I hope you'll join me in thanking all of our fabulous panelists.